Hello everyone, welcome to COMP251, Data Structures and Algorithms. This video basically is going to be an intro to the course. I'm going to just give you a brief overview of what we are going to learn in this course and briefly talk about the concept of abstract data type. And these are the information about me. All the informations about the course are available in the course outline on Blackboard. So I'm skipping those information about the exams, assignments, lab, quiz, and this sort of stuffs. So the office hours for this course is going to be Tuesdays, 9 a.m. to 11, and we are going to have some meetings on Thursday as well. Okay, so about this course. This course is going to be, a programming level course. I mean, this is still you are going to learn about programming in this course, but this is also going to cover some sort of algorithms as well. So kind of this course is going to be an intermediate level course on algorithms. In this course, you will learn about different practical and important data structures and different methods, how we implement them and how we use them in some real applications. Basically, in this course, you will learn how to write better programs and solve problems efficiently. So we are going to learn problem solving, computer science problem solving. So when I'm talking about the problem solving in the context of computer science, so this is going to be the process of taking your problem, the statement of your problem, and you just develop a computer program that solves this problem. So it's going to have two main parts. You are going to design an algorithm, which is going to be a step-by-step specification, a sort of instruction that you tell the computer what to do. And you also need a data structure, right? Basically, every algorithm that you write is going to work on some data. That data needs to be stored somewhere. So we are going to learn about different data structures that helps us to write more efficient algorithms. So this course not only is about algorithms, it is also about the data structures. And you will actually see that there is a close relation between these two parts of a problem solving. Any problem solving technique, you need to have good algorithms and you need to have access to efficient data structures to be able to efficiently solve a problem. The prerequisite for this course, it is clear you should have a good knowledge of programming. So you should have passed the object-oriented programming COMP251. And because we are analyzing the efficiency of algorithms, and we should have a good understanding of discrete math as well. You will see that through this course, everywhere we are actually referring to the concepts from discrete math, which is going to be Math 125 in UFE. And we are going to use Java as the programming language that we do the lab exercises and assignments. The topics that we cover is going to be first, we will learn about different abstract data types and data structures, lists, different implementation for that using arrays, linked list, stack, queue, which are some variations of a list with some restrictions over the operators, a heap, different type of trees, dictionary, or actually it's going to be a hash table. We will also learn how to analyze and analyze the efficiency of the algorithms in terms of the space and the time. So Basically, the next topic that I'm going to talk about is going to be asymptotic analysis. It's going to be a tool, a mathematical tool that helps us to analyze the efficiency of algorithms. This tool will be used to analyze the efficiency of algorithms in terms of time and space both. At the end, we will also cover some the well-known sorting algorithms like quicksort, merge sort, and heap sort. We will also talk about famous searching methods like the binary search, ABL trees, and hash tables. Okay, about the reading, I tried to make the lectures in this the set of slides to be self-contained, but it's always good to have a textbook. For this course, I decided to use the data structure and problem solving using Java by Mark Weiss, the 4th edition. So you can get it from the bookstore, or I believe it is also available in the library. Okay, so before I finish actually this set of slides here, I wanted to show you some example of problems that we will solve, and in this course you will learn about the data structures that helps us to solve these problems efficiently. I have actually listed 3 examples here. The first one is that think about this problem that you have an input string which is going to be an expression. In fact, this is a string. And you wanted to check if it is balanced in terms of brackets or not. For example, the first example here that you can see, this is balanced in terms of the brackets. If you actually check it, you will see that everything is balanced here. But this one is an example of unbalanced expression. Okay, how can we solve a problem like this? If you are not familiar with the data structures, just you are familiar with what you have learned in the introduction to programming, you probably would think that, okay, I should, in introduction to programming, you have just learned about the primitive data types and kind of, for example, strings, and that's it. So in that case, if you wanted to solve this problem, you would probably need to use an array, and solving this problem is going to be very inefficient and time consuming. Although if you know about a very famous data structure stack, we can actually write down a very efficient algorithm to solve this problem using a stack. Basically, this example is going to be one of the examples that we solve in class, so I'm not going to talk about it more here. Just on your own, just think about it, how you are going to solve this problem without a stack. How to check if the brackets in an expressions are balanced or not. Another example here is, for example, you wanted to implement a scheduler for a printer, or basically any other server that is going to get, a set of queries from different clients, and you wanted to actually just schedule these jobs, these tasks. And not only you wanted to schedule them based on the time that, for example, this query came earlier than this one, so I have to actually answer this one before than the other one, but also a kind of priority has been defined for these queries as well. For example, you know that this query is more urgent to be answered. For example, you are implementing a scheduler for a printer, and you wanted to minimize the waiting time for all the jobs. For example, if you have 3 jobs, like one has 10 pages, the other one has 1 page, and the other one has 100 pages. Which one you should do first? So if you are actually implementing a scheduler you basically need to have a queue, and if you have some metric to define the to define that, for example, this some of the jobs are more urgent than the other, you wanted to actually just prioritize them over the others, you need a priority queue to implement this. Otherwise, the implementation is going to be very complicated and very time consuming. But we will learn about a data structure that we call it a priority queue, and we can see that how efficient this data structure makes the algorithm that we write to implement the scheduler. The next example here is, assume you have an expression like this arithmetic expression, and you wanted to evaluate an expression like this. This is something that basically any compiler would do. How we can evaluate an expression, some arithmetic expression like this, with the parentheses, with the, having this fact that some operators are going to be more, has higher priorities than the others, and many other actually rules. So we will learn in this course that how we can implement a very efficient algorithm to evaluate this kind of arithmetic expressions using a binary expression tree. So we learn about some data structure which is a tree. It's basically called a binary expression tree that helps us to evaluate this kind of expressions. So the whole course is in fact about different type of data structures, how they work. Not only we learn where we can actually use them, not only we learn about their properties, we learn how they have been implemented, and so we learn when we are actually getting a new problem, how we can design our own data structure for the problem just based on the properties of the problem that we are solving. So we learn about many different data structures, and based on that we also actually learn that how they have been implemented. We learn to analyze the efficiency of the algorithms. This is a must, so that you would understand that this structure is going to this data structure is going to work better than this structure under this condition. So you need to have some kind of a metric to analyze the efficiency of the algorithms as well. We will also learn about many well-known sorting algorithms, which is, sorting is a very, a procedure that is used in many actually problems that we solve. So that's why we need to know the best sorting algorithms which are possible. Basically all the built-in sorting algorithms in different programming languages like Java, C++, Python, they are some form of the sorting algorithms that we are going to learn here. Okay, so I have actually more slides here. You can check them later. They just give you, a kind of a history about the algorithms and why we study algorithms and so on, that I'm going to actually skip them here, but you can check them out later in the slides. So I'm going to continue this lecture by talking about containers or abstracted data types. Where is it? Containers. Okay, so when we are solving any problem, the fact is you are working on some data. Okay, that data needs to be stored somewhere in the computer. So basically anything that you do on the computer is kind of, some form of information processing. And so storing the data and then retrieving it is going to be the main part of the process that you are doing on the computer. It doesn't matter what is going to be that process. Okay, so that is very important, that how we store that data in the memory. Are we going to just use the primitive data types like the integer, Boolean character, and are they enough actually? You know that at the end, the computer, everything in the computer has been implemented as a 0, 1 in a form of a binary. But for you as a user, as a as a programmer, if you are going to write down all your codes in basically just in binary in 0, 1, that's going to be very complicated, right? You know that we have implemented the different higher level programming languages because it is going to be hard to work and write down the programs in based on the assembly or for example the binary code. But still, if you are going to use write complicated programs, just using the primitive data types like the integer, Boolean, character, or a string, are these data types enough to write very complicated programs? They are enough, but when you are actually designing more complicated type of data, you make the programming much easier. So basically, when we are talking about the abstract data type kind of is against the primitive data types. Primitive data type is a type that, for example, like just an integer number or a Boolean, just true, false, or one character that you store. In abstract data types, you are talking about a more complicated type of data that has some behavior. For example, a list of items. Don't confuse list and array. Array is a fixed space in the memory. Okay, for example, you would take an array of size 100. Okay, this is a fixed size of the memory. You just know that, okay, I have access to an array of size 100. But how many data you have, how many items you have stored in the array, the array doesn't tell you how many items has been stored for it. You just know that the maximum size is going to be, for example, 100. But if you have only stored 2 items here, okay, you should also keep track of, you should keep another array, another variable to just tell you that, okay, how many items has been stored here? Okay, just 2 items. If you add another item here, you just need to update this and say that, okay, no, I have 3 items in the array. But a list is an abstract data type that tell you that, okay, I have a list. At the beginning, it can be 0. Then you have added 1 item to it, so it's going to be just 1 item. Then you have added another item. This is going to be, okay, no 2 items, no 3 items, right? So a list is different than an array. Array is kind of a primitive data type. I don't mean the primitive data type in Java, but array is kind of primitive. It doesn't have any behavior. It is just, a space in the memory. But an abstract data type is going to be, how can I, okay, got rid of this menu. Abstract data type is a type for storing the data that has some behaviors. Okay, it is more complicated. It's just like you are working in a higher level than the primitive data types that you store. So abstract data types are going to talk about different models of storing information in the memory and how we access to that information in the memory. The most general form of an abstract data type is going to be a collection, or we call it a container. These 2 names, collection and container, I'm actually using them interchangeably. In Java, Java Collection API or Java Collection Framework, this is called collection, but in some In many textbooks, they call it a container. So container or collection both refer to the same concept. So a collection basically describes a structure that store some data and allows us to access the data. And each abstract data type, each container basically follows some specific schema for accessing the data. For example, a card deck is going to be a collection of cards or a container of cards. Or for example, a dictionary is a collection of words. You see that a container is going to be a structure that stores a set of items, objects, that the type of all of those objects are going to be the same, and a specific type of relationship between those items will be preserved. Okay, so let me actually give you some sort of definition from the Java collection. I have actually quoted this one from the Java collection framework tutorial. It defines a collection to be a collection, sometimes called a container, is simply an object that groups multiple elements into a single unit. Collections are used to store, retrieve, manipulate, and communicate aggregate data. Typically, they represent data items that form a natural group, such as a poker hand, which is going to be a collection of cards, or a mail folder, which is going to be a collection of letters. You can see that the type of all those items are going to be the same type, and there is a kind of relationship between them. Or a telephone directory, which is a mapping of names to phone numbers. So a telephone directory is going to be a set of names corresponding to a set of phone numbers. So everything about a collection or a container is basically about the data that we store inside them and the type of queries or behavior that we define for that collection. Those queries that we can run over the collection can be divided to two different sets. Those queries that works over the container as an object, as just one entity itself, or those that works over the items that has been stored inside the container. So let me actually show you some example of the operations that we define over a collection as just one object. For example, creating a collection, copying a collection, removing a collection, empty a collection, or check that how many items has been stored in a collection. Or for example, you have two collections, you want to just get the union of these two, or check that if there is some intersection between them, or check if these two collections are the same, are equal, basically they are storing the same set of items. So all these operators, all these queries are basically working over the collection as a unit, as an object itself. In Java collection framework, we actually try to use the same name for those, there are many different collections have been implemented in Java. But for all of them, they try to actually follow some name schema. So they use basically the same name for the same operator has been defined over different collections. So always we use actually the name, for example, clear to empty a collection. Or for example, the method is actually called size to check how many items has been stored in the collection or container. Or the method is empty, just basically returns true false, tells that if the collection is empty or not, is there any item has been stored in the collection or not. Or for example, add all It's just like you have a collection, you wanted to add every item inside this collection to another collection. Okay, so you pass it, and it's basically add and kind of merge all those items from the collection C into the one that you call the method over it. Or for example, a method that check if the two collections are equal or not. Remember this name equals, the method equals that we have talked about it in the Java review section. The other set of operators that we define, queries that we define over the collections or containers, they work over the items that has been stored inside the collection or container. For example, insert this object inside the collection, remove some specific object from the collection, check if the collection has this specific item. I mean, this one item I have, and I wanted to check that if it exists inside the collection or not. Check to for example, give an access to this specific collection. Let me actually just modify that specific collection, or this kind of operators. Again, for this kind of operators in Java, we have a sort of some kind of name schema. For example, we usually use the name add to add an object to the collection, remove to remove an object from the collection, contains, that again is going to be a Boolean method which basically return true false if after checking that if an object exists in the a collection or not. These iterators are basically just allows you to, for example, iterate over all the items inside the collection. When I'm talking about a collection, I'm not talking about an array of data. Okay, for example, your collection might be actually a tree, so iterating over all the items is a query which is important for us. In some cases, your abstract data type, your collection is a tree, but you still wanted to just iterate over the items, so the iterator allows you to iterate over the items in that case. Okay, the operations that you define over your abstract data type will depend on the data structure that you are implementing. Sometimes you are implementing some specific data structure. For example, you are implementing a stack. So in that case, the operations that you define will be just those operations that has been defined for the data structure stack. But sometimes you are designing some data, I mean, most of the time you are designing some new abstract data type depending on the problem that you are solving. So this is your design. You would actually probably guess that, okay, I need to have a tree and I need to define this kind of queries just based on the problem that I'm solving. Okay, in this problem, I would need to access to the data in this specific form, so I need to define some specific form of a query for my abstract data type. So all is about the design of this abstract data type, and sometimes the well-known data structures are going to be enough to solve a problem, but sometimes you might need to actually just modify those data structures or add or remove some of the methods from the abstract data type. Another aspect that basically will affect the design of your abstract data type a lot is the relationship between the items, between those objects that you have stored in your containers or collections. So when you are actually storing your collections, a set of items in your collection, most of the time there is a relationship between those items. For example, if you have created some genealogical database, you don't want to actually just keep the information of a couple of actually different people. You wanted to keep the relationship between them as well. That, for example, this one is a parent of this one is a child of the other one, this one is a these two are sibling, and this kind of relationship needs to be stored as well. Basically, if there is no relationship between the items that you are storing in your collection, one form of data structure is going to be enough to use. If there is no relationship between the data, you don't need different type of abstract data types, different type of data structures. Only one data structure is going to work, and that data structure is going to be called hash table. Because if there is no relationship between the data, the only type of queries that you are going to do over the set of items that you have in your container is that, okay, insert this item in the container, remove this item, just check if the item exists, and that's it. So only accessing to those items. There is no relationship between the items. Actually, let me give you I forgot actually to mention this fact that hash table is a very useful data structure. The good thing about the hash table is that if you have implemented a good hash table, for example, Java has a lot of, all the programming languages have some built-in, data structures for hash tables, that although hash tables are using more space than what is required, for example, you might actually want to store only 100 items, but usually the amount of space that would take is going to be around 30% more than what it is required, but it gives you access to the data in a very fast way. It actually gives you access to the data in almost constant time. If you haven't heard about the hash table, you don't know how it works, let me actually give you an example in real world to make it more clear that how the hash tables, what does the hash table to do, and why we say that the hash tables are very efficient in terms of time. So assume that you are going to implement a mailbox for a department which has 12 staff, but you know that the staff is frequently changing. So if you are going to implement a mailbox here, you would probably create a mailbox of size 12 because you know that the number of staff is going to be fixed, right? And then you just created some labels for each one, some label name for each one. But because the staff is changing, you have to keep creating some new labels. Each time that someone is adding or someone is removing, you should change the labels. Okay, so now you can see that the cost of maintaining such a mailbox is going to be very high. You have to actually assign someone to just update the label of the mailboxes. But what we can do is that, and usually in the everywhere you actually see this, is that instead of creating a mailbox of the size of the number of staff, you can create a mailbox of size, for example, 24. You can see that I have actually covered some of those letters have been combined, like P and Q or X and Y, which are less frequent. So you can have a mailbox of size 24. You can see that I'm using more space, and I would label all of these boxes with a letter, not the full name. So the mail of each person is going to go with the based on, for example, the family name, the starting letter of a family name, and you never need to update the label of the mailboxes, although you are using more space, but you are actually making the access and the cost of the maintenance to be zero, which is very efficient. This is a concept of a hash table, that you are using more space, but access to every item that you are looking for is going to be very constant, and you don't need to actually spend more time to update and maintain the whole collection. But unfortunately, in many real-world problems that we solve, hash tables are not going to be enough, because we need to keep some relationship between the items. For example, assume you are implementing some kind of waiting list. For example, for the the registration office of that implement some waiting list for different courses. Okay, so in the waiting list, you wanted to know that which person have been waited in the list the longest, so that you wanted to actually let them register in the course first. So there is a relationship between items. You don't have just a set of names and without any relationship between them. There is a relation. This person have been weighted more than this person. This person has been weighted more than the other one. So this is a kind of relationship between those items, and a hash table cannot help us to implement a waiting list. Or for example, you wanted to implement a compiler. A compiler actually, which is compiling an object-oriented program. There is a relationship between for example, the classes that has been implemented in a code, that this class has been derived from the other class. This class has implements this interface. So there is a relationship between these different objects, right? Or for example, you wanted to, again, about that application of the registration for the university, you wanted to actually keep some relationship between the courses, that this course is the prerequisite of this course. If someone has failed in this course, cannot register in, for example, COMP251. And this kind of, so there is a relationship between these objects. You wanted to implement and keep those relationships. So based on the type of relationship that you wanted to preserve between the data, we can divide our containers to 3 different categories. These categories are not going to be exclusive. They are not actually covering all possible type of containers or collections, but they are covering most of important ones that we care about in this course. So the first set of containers or collections are linear collections, which keep linear relationship between the items. So in this case, when you are actually keeping a set of items in your collection, you know that, for example, this one is first, and after this one you have this one, after this one you have this one. So a kind of linear relation between the items exists. So for example, if you have a set of numbers, the integer numbers, they have a kind of linear relationship between them, right? Or for example, if you are going to implement the memory has some addresses, and there is a linear relation between these addresses, right? So those data structures in this type are going to be arrays, a list, a stack, queue. We are going to learn about all of them next week. Not a stack and queue. A stack and queue is going to be the next week. But anyway, these are going to be the simplest form of collections, containers that we will learn about them. We start with the linear containers. Hierarchical containers are basically in this form, that one object is going to be the root. From the root, you would have access to some other items. It's just like you are going to have access to the items in the next level, and it gives you in a form of a hierarchy. Basically, all hierarchical containers is actually implementing a kind of a tree, a rooted tree. That one item is going to be called the root, and from each item you have access to a couple of other items, right? And you can see that this is a kind of creating a tree. This is not a graph, because, for example, you cannot, for example, from here have access to this one, or there is no relationship between this one and this one. Okay, if there was a relationship between these two items, it is not going to be a hierarchical container. It will be a kind of a graph. Where we are using hierarchical containers, all the trees are going to be hierarchical containers. For example, binary heap, binary tree, binary expression tree, binary search tree, AVL trees, and some example of what we are going to do with them. For example, that implementation of a for the compiler, when you are going to compile an object-oriented program, you would preserve the set of all the classes that has been created and derived from each other in a form of a tree. And the last type of containers are going to be those which are in the form of a graph. So the items in a graph can have a relation with all other items in the graph. We have two different type of graphs, undirected and directed. If your graph is directed, it means that if there is a relation between this one and this one, it doesn't mean that you have a relation, from this one back to this one as well. There should be another link to preserve that relation. So my example of directed graphs is going to be, for example, World Wide Web. In World Wide Web, every page is going to be an object, right? And each page might have some hyperlink to other pages, and all these links are going to be directed. An example of undirected graphs is going to be, for example, in a social media like Facebook. If like Jane is friend with Ryan, Ryan is also friend with Jane, right? So these relationships are going to be undirected. So the whole graph is going to be undirected. Some other examples of the graph is, for example, all those applications like the Google Map, any map that is going to find a kind of a direction between two different points. Usually they have implemented it using a graph. For all different points, you have an object, and the routes, the streets which are connecting these different points are going to show actually those relations between them. We should know that actually, again, these relations between the items will be defined in your problem, that the problem you are solving. Sometimes these relations are given explicitly to you. For example, if you are designing some, some software for a company, the relationship between all the staff, the relationship between them is explicitly given. For example, this person is going to be CEO, this person is going to be CTO, this person is COO, this person is senior manager, this person is a manager, this person is a developer, this one is a tester, this kind of information. But all this information will explicitly given. Sometimes this information they are not given explicitly. For example, if you are working on a set of numbers and you know that they are going to be, you should keep them in a sorted way, or you care about the size of them anyway. So the relationship between those are kind of implicit, right? They are not really explicitly given to you. So when you are designing and when you are choosing the best abstract data type to solve your problem, you should think that about the relationship between the objects that you are storing in your collection. Okay, so kind of to summarize this lecture, anytime that you wanted to actually store a set of items in a collection or in a data, or you wanted to actually design your abstract data type, before choosing the best abstract data type, the best data structure to store your data, you need to basically answer a couple of questions. That what is the relationship between these objects? What type of queries might be asked about the items inside the container? What type of queries can be asked about the whole container as an object? What type of operations needs to be performed over the container? What type of relation or queries, what type of queries might be asked about the relationship between these items? Okay, after answering all these questions, it actually gives you a sense that what is going to be the best data structure to store the set of items that you have. Okay, so mainly throughout this course, I'm going to show you different data structures, how we implement these data structures, what are the properties, what are the operations that we can define over these data structures, how efficient these operators can be implemented for the data structures. And so after you learn about all these stuffs, whenever you are going to solve a problem, you should actually refer to this set of all these different data structures that you have learned and find the best one. So by the end of this course, if for example someone asks you a problem that inside that problem you needed to keep a set of items sorted, so a kind of that's going to be a sorted abstract data type. Okay, you wanted to have a set of items and you wanted to keep them always sorted. Just think about it in this way. Probably if I give you a problem like this now, you would choose an array to store your data. But by the end of this course, I hope that you choose a better data structure, not a simple array. Because we will see that if you are going to use a simple array, the cost of keeping your items sorted in a regular array is going to be very costly. So I hope after 4 months in April, you have a better answer for this question. You choose a better data structure which works in a more efficient way to store and keep the data in a sorted way. The last actually thing that I wanted to mention here is that we can also divide the abstract data types, the collections, the containers, based on this fact that they are simple or associative containers. Most of the data structures that we discuss in this course, they are going to be simple containers. By simple container, I mean those containers that each object that you store inside the collection is going to be independently stored. By independently, I don't mean that there is no relationship between the items. There is a relationship between the items, but each item is independent of the others. But in the associative containers, for example, for each item, there is some associated key. For example, if you are implementing a hash map, usually for each item there is another object of a different type, which we usually actually call it a key. So simple containers are going to be like the list, the stack, queue, even most of the trees are going to be simple containers. But associative containers are going to be usually map, hash map, and anyone that along with each object you are also keeping some keys associated with that. Okay, usually in Java, we divide the there is a large set of collections implemented in Java that we call it Java Collection Framework. It is available in Java Util. Remember, we have actually used the arrays from this Java Util. All of those different collections implemented in Java are available in Java Util. And so most of these data structures, not all of them, but most of the data structure that we discuss here, like the stack, queue, DQ, these have been implemented in Java. You can actually use those data structures. Hash map, set, all of these have been implemented in Java. You can use those ones. In Java Collection API, they have actually divided based on 3 major interface: list, set, and map. So they are not basically about the topics of this course. I just wanted to talk about this to you because we are going to use Java, and I want you to be a better Java programmer actually at the end. So list, they are going to be those collections which basically keep the data in a linear order. In this interface, be careful, list is an interface. This is not going to be an actual class, but all the array list, stack, queue, deck, all of them are going to be implementing this interface list. So they all have these properties that they keep the data in a ordered way. There is a linear relation between the items. You may have a duplicate elements in the lists, and there is going to be some kind of index associated to the items, kind of like the array. These are going to be 0 indexed, and we are going to next week learn about the first type of abstract data type. We call it list, and 2 different implementation for that. The other interface is called set. Set is actually a collection which keeps a couple of items, and there's only one occurrence of each item. So basically you cannot have a duplication in the list. In the set, it is something kind of similar to set in math, that each item is going to be unique in the set. Some specific kind of set is called sorted set, which has a lot of actual applications. Keeps the item in a sorted way. It is a set, but it keeps the items in ordered way. And the last one is going to be map. So maps are going to have a key and a value. These are going to implement all the hash tables. Hash maps are going to implement this interface map. If you need to create a dictionary, for example, where you have some words, and for each word there is some information. So kind of you have a word, you have a key and some value. You have a word and the definition associated for that. This is going to be probably implementing this interface map. So this is the end of this lecture, and you can actually study chapter 6 of your textbook for this lecture.